Okay, let's start this lecture. This is lecture 25 and we will continue our discussion on oscillators. Okay, so let me just use fine. Okay, so at the very end of the last class, we were looking at differential cell, which is used as a unit cell for an oscillator, and this one is I naught, this is in and in bar R, and this is out and out bar. Okay, this is what we saw. This is a cell which is used. So let me just make this. Oh, bad. So, okay, so this is positive, negative. Let me just write it as positive, negative. So this one should be crossed and connected to here, and this is connected here. I put as an even, so let that be the case. So this is one cell of the oscillator. Okay, so we started looking at tuning frequency, or let's say frequency range, how to tune the frequency for this oscillator. Okay, so the first change in this particular oscillator cell to vary the frequency is we replace the resistor. So we found out this thing. Let me just okay, so F oscillator, or frequency of oscillation, is inversely proportional to R on times C, and since the resistor which we are using in order to change the frequency, it's a MOS resistance. So this one is, I am just using a MOS resistance with a control voltage V control connected to VDD, and this is one of the output nodes. Okay, so this is R on C is equals to 1 over C times you have kW by L into VDD minus V control minus mod VTH. Okay, with the first order approximation. So we saw till in the last class we saw this, and V's output swing is equals to peak is equals to 2 times I naught into R, because here the output swings are somewhat bad. So one node goes to VDD, another goes to VDD minus I naught times R on. So this is single-ended swing. So the differential is I naught times R on. Okay, and F oscillator is inversely proportional to R on. So this is 2 I naught, or you can say this output swing is inversely proportional to F of oscillation. So let me use a smaller f here. So frequency of oscillation, or let me write this here. F oscillation is frequency of oscillation. Okay. So we saw in the last class we saw till here, right? So one thing is, so if you see, let me just point out what are the things here. So f of oscillation is inversely proportional to R on, okay, and directly proportional to minus V control. Okay, then output swing is inversely proportional to frequency of oscillation. Okay, and the other thing is you need to keep transistors in linear region. So this will limit your range for V control and oscillation frequency both. How much can you vary? Okay. So for this particular cell which is used in the oscillator, we have these are the observations. Okay. Now one thing which you can say that if I am having the output swing of the oscillator is inversely proportional to oscillation frequency, that doesn't sound good to begin with. Reason is, so okay, this also has a limited swing. The same thing, right? Limited output swing. So you're using these clock outputs to clock some of the digital logic, which can have a variable input clock frequency. But if the amplitude changes, you need to get the whole logic as per the changing amplitude. Okay, and if if your amplitude is inversely proportional to oscillation frequency, you get more susceptible to noise at a higher frequency. Okay, so let me just for an example, so show you. This is not that mathematical, means I will show you more on a qualitative manner. So one is this sine wave amplitude and the other one is, let's say, this one. Okay. Okay. So if I apply a disturbance at this node by a certain amount delta, right, and it changes the phase, it is, so it is like, so let me give you a more. So what we want to compare is whether the oscillation with the lower amplitude is more susceptible to the same noise or a high oscillation with the higher amplitude. Okay, so this is a very first order approximation which I am doing. So I have a sine wave, okay, and I apply a delta change here, which will apply, if I apply a delta change here, this will cause my sine wave to slightly move away or before. So in this case it will move before because I'm pushing that. So let's say it becomes like this. So okay, let me draw it a little bit more clearly, this one, sorry that. So let me just do it this way. Okay, so this is very amplified version of the sine wave near time t equals to 0. Okay, it has a certain slope. Now I am applying a change delta here. Okay, so there are two things which I am considering. When the, and you know that the slope of the sine wave at this point is directly proportional to amplitude. So V in, okay, so let me just write it here. V in is equals to A sine omega naught t, okay, and dV in by dt, which is the slope, is A omega naught cosine of omega naught t. So slope is equals to A omega naught. I consider two cases where your amplitude is smaller and the other case amplitude is larger. Okay. So in one case where your amplitude is larger, if you apply a certain delta V, so let me make this thing. So delta V is the change which you apply you want to calculate what is the phase change with respect to that. Okay, so effectively, so what that's, if you do not get it, just let me know. So the thing is, I'm applying a change to, if I apply delta V, you make a shift. Okay, so what is the phase change which you get? So means this particular trick is used at many different places. How do you take the noise contribution into account for a periodic systems? So here I am just trying to show you that for, so this is delta V and noise we applied. This is delta T which we want to calculate. Okay, and the slope is dependent here on the amplitude, whatever the sine wave is. So in which case you will see the delta T will be larger. So if I say A1 is greater than A2 amplitude and I ask you delta T1 and the same noise is injected, what should be the sign for this? Huh? If slope is very high, what will be delta T? Why? Slope is equals to delta V in by delta T, right? So slope is equals to delta V by delta T here, right? So it is inversely proportional to the slope. If the slope is larger, then your delta T change will be small. Okay. So, okay, this is a very rough way of telling you, but this is the way it will be if you apply any change here. You can calculate it very much more methodologically, but this is just to give you the idea. Okay. So, in this case, if A1 is greater than A2, your delta T1 will be less than delta T2. Change. So, one other drawback of this oscillator when it has a limited output swing is actually the poor phase noise, okay, which comes of both the reasons that you're having a limited output swings. That's why also you are more susceptible to the edge variations. And the other thing is, in this case, both the transistors are always on. So they are contributing to the noise all the time right now. Okay. In this case, if I am able to increase the amplitude, I will get a lower phase noise. Yeah. No, susceptible to high noise, more susceptible to noise. Yeah.
That way also it would be dual loss if we have a kind of small amplitude or
No, so the thing is, okay, so the confusion is this. Here, the delta T change which I am causing, that is, which I am having because of the amplitude, is actually for a lower amplitude, I am having a larger delta T change. That's the disturbance which you are having. Okay, now the next question is that the phase noise which is defined is always defined as minus dBc, which is with respect to the amplitude. So will it cause me for a lower amplitude higher noise? Means another additional effect? No, no, not in that way. So okay, let's look at that. No. So let me see. So I am having a carrier in two cases. One is this. Okay. Now the disturbance because of this phase noise, you need to see the whole. First thing is you need to see the whole conversion. How the at delta f, what is the amplitude relation, right? So at that delta f, you will, if you take this, so okay, so first thing is don't relate it directly from here to what you see in the spectrum. So this one is, how shall I treat it? So you remember using V out of t, let me start here, as something as A of cosine of omega naught t plus another sinusoidal factor. So let me just call as Vn cosine of omega some, let's say omega 1 of t or delta omega t. Let's just put it that way. Okay. So in this case, if you're plotting this particular thing, as your A reduces, your this thing will also go down. Means you can work this out. It is dependent on the noise amplitude and Hall, right? The way I have written is that I am changing the phase here with respect to Vn. Okay, that's a slightly different thing when I am talking here. If I apply a Vn amplitude and I am changing this delta t, so I need to find. So okay, let's see here. So in this case, okay, so what is here, delta t is equals to delta Vn by slope, right? And which is A of omega naught, if I am just considering here. Now this relates to your phase change as 2 pi delta t by t or whatever it is. So you have 2 pi Vn by delta t by t. This is omega naught by A, right? Okay, so now right now this doesn't have any variation, but you will have a variation on this. Now this becomes the amplitude when it comes here. Okay, so need to see the whole conversion as such. As far as I see that you will have many factors which are coming. So whether it is a double change, I am not so sure of that. Okay. So means when you are relating this time domain picture to the frequency domain and all the modulation, be careful that, again, I told when I talked about this is the way you can relate to it. Okay. But how exactly quantitatively it is coming, you need to work out all the things. So now since you are talking, so whatever, let's say, this is again interesting part. So I am having Vn, I am considering all the noise which is injected here, right? That is causing me a actual phase shift. Then the signal which is affecting the sinusoidal is not, so okay. So the signal which is affecting the sinusoidal are periodic with respect to this at period, right? And these are also random variables right now. They can pick up any value, but they are coming all at that time. So let me just write as Vn of t. Now this Vn of t causes you a phase change phi of t with relation to the amplitude factor here. Okay. Now this is a phase change which will appear here. Then you work that out. So you will surely find the relation with respect to A, but let's do it more qualitatively if you want to see what exactly change it will be. Okay. So this is the side part right now. So all this analysis is comes under impulse sensitivity function analysis. We are not going through that, but you can always look at the reference paper. That, so since we have brought this here, so let me just show you. Okay, so in order to find how the noise, okay, it's not coming sinusoidal. So your oscillator is periodic with the time, periodic with the whatever the frequency of the sine wave is. Let me just do it this way. Okay, I think you read this paper, but I will tell you what the whole thing it is doing here. So and in an actual system you are having a noise all the time, means whatever the noise is coming. Okay, now how this noise is going to change the output sine wave, which might be something like this, whatever it is going to change the amplitude and the phase both. So if I find the response, means if I have this oscillator, so let me just say, you see this is a very non-linear, first thing is a very non-linear translation. I am having the voltage, I am causing the amplitude to just change, and that voltage is changing the phase, and the final value is this. Okay, so what you do, you find how if I cause any disturbance here, how my phase changes. If I cause any disturbance here, how my phase changes. So you find all the change in the phase with respect to the different timings of the inputs. This comes under impulse sensitivity function. So this is called ISF, impulse sensitivity function. Okay. So you on this periodic wave you find the output phase noise with respect to the input voltage. This includes all the kind of frequency translation which will be happening. Because it's a periodic system in the end. And then you find the total phase noise. So what I have just talked about is about one location. The actual phase noise at the output is dependent on all the locations. Okay, so that is, I think you can read a paper. This is by Thomas Lee and Ali Hajmiri. It's a 1999 or 2000 paper. And this is about the ring oscillators specifically. There are also the theories which prove that whatever they suggested is not valid in all the cases. So it is only valid in few, like restricted amount cases. Okay. So any questions? Yeah. Higher amplitude is less susceptible to noise. And you will see this thing in many means. That is why I just brought up this kind of rough picture where you can also understand if the slope is larger, I apply a delta change, it is going to be lesser or more. No, we are comparing of the same frequency. So if you see in this particular oscillator, right, what is happening? At a higher oscillation frequency, your amplitude is reducing. Means without doing any math, this doesn't sound as a higher frequency. I want to be less susceptible to noise also, and I should have a higher amplitude. Why a lower amplitude? Okay. This may only help that, okay, if at a higher frequency of oscillation you are having a lesser amplitude, it may reduce the or maintain the power consumption. I mean, this is just so power consumption in any digital logic is dependent on the amplitude and your oscillation frequency, right? So this is opposite. As the oscillation frequency goes up, your amplitude goes down. So any of the capsules which are charged and discharged at every oscillation frequency, now they are charged and discharged to a lower amplitude. So power consumption is not directly proportional to the F oscillation in this case. But that is not the requirement. That is somehow the drawback here. Okay. So any questions on this? Okay. So what we want to do is we want to have V out swing independent of oscillation frequency or may be directly proportional. Okay. One way you can always say I can amplify this oscillation amplitude with some amplifiers and always maintain the same amplitude. But if you are going to do that, that particular block itself will add the noise. So right now we are looking for having a same output swing independent of the oscillation frequency. Okay. So what we have V out swing is 2 times I naught times R on. Okay, and since R on is inversely proportional to F oscillation, this get inversely proportional to F oscillation. So if I want to make it constant, what shall I do? I have to vary R on to vary the oscillation frequency. Pardon? Change I naught also, right? So one way to change I naught will be, so let's say I have, earlier I had this as a MOS in Neelian region, which is used as a resistor. So let me just draw this. Okay, so IN and IN bar, and this was I naught. Okay, so what I want to do, I want to change the I naught with respect to my R, or R with respect to my I naught, whichever way you want to take it. So one way to do this is, okay, so let me just write right now this as VB. I will tell you what this signal will be. So let's say this is I naught, and I connect these two also together. So let's first connect them together, and the current is I naught. Okay, let's make sure that M0, M1, and M2, they are in linear region. Okay, so your I naught, I can write this as, if the op amp works fine, then the VDD minus Vref by R on. Okay, so here your V output swing is now equals to your 2 times I naught R on is 2 times VDD minus Vref. Okay, yeah. No, let it be in triode, right? It is, the gain will be lesser. You can have the another op amp with the larger gain to make it right. So that is not the case. That is not the problem as such. Okay. So, huh? I didn't get you. Yeah, the only part which is in feedback is means this is the cell. This is just the bias section. I use the bias section to get a certain R on. Loop gain will not matter to the fact that if this is Vref, what is the Vref? What is the difference between Vref and Vref dash in any practical case? So your loop gain will matter, and because you are using the transistor in triode, so that will have a lower gain. Okay. So now your output swing is fixed, right? Now how do I change my oscillation frequency? So so you see, right? If I change I naught, I change R naught. Oscillation frequency is dependent on R naught and whatever the capacitance which is coming here, right? See. So if I want to change the oscillation frequency, I have to change here I naught. Okay. Or the other thing is I change Vref, whichever way. Okay. So in this case, I will go, and that's why I say in place of VB, I use V control. Okay. So Now let me write it. So let's say whatever V control you have for a given V control and I. So for a given V control you have I naught. So let me call this as V control 0. You have I naught, and for a given I naught you have a resistance VDD minus Vref by I naught, and this will basically give you the oscillation frequency. F oscillation is inversely proportional to R on C, which is, and R on is your what? VDD minus Vref by I naught, and this is C. Okay, this is your R on. So just see the flow, that which signal you control and what it leads to. Okay. Now if I want to change the oscillation frequency, okay, let's say delta F. So in order to change this, okay, let me frequency tuning. So for frequency tuning, I will vary V control. Okay. So your delta F is inversely proportional to delta I naught by VDD minus Vref times C. Is that fine or anything? Okay. And your delta I naught is GM times V control. Okay. Huh? No, no, no. I naught does not control a Vref by M naught. Means I will change the control voltage here. V bias. Let me just call this as VBP. I will change VBP depending on I naught. Means Vref has to take into account that this transistor has to be always in linear region. That is a separate part. Okay. Vref cannot be anything. Vref has to take the linearity of the transistor into account. So in this case, you have frequency of oscillation or delta F of oscillation is directly proportional to V control, in contrast to the previous one, which was inversely proportional to minus V control. And your V out swing is fixed to 2 times VDD minus Vref. Okay, and Vref should ensure linearity of M0, M1, M2, whatever the transition linear region need to be. Okay. Now another thing which is which you can say that the the control from V control node to I naught may not be linear. Okay, because you will see the drain channel length modulation effects, so that may not be linear. So what can you do to make the V control to I naught linear? And this is yeah, put a cascode. You're putting a cascode here. You will need to put a cascode in the cell also. That may not be that desirable. So means this is a simpler one, right? You use a resistive degeneration to get a to change that. So a simple resistive degeneration can be, so let's say, okay, whenever I draw this side it doesn't come right. Okay, so let's say I generate Now this can be R external or something. You again need to see because you have to fix this R either and control N. And now I change this to V control. Okay. So then delta of oscillation will be dependent on, you can say that this nominal current might be, can be I naught. Okay. So now the current will be V controlled by, let me call this as Rx. Okay. So in this case, your delta I is equals to delta V control by Rx. Everyone knows, right? This resistively degenerated amplifiers, they have the much more linear as compared to the common source ones. Okay. So far for this limited swing one, we see that we can have a fixed output swing and a linear control to an extreme. Okay. Now there is another problem with this kind of cell. So let me just highlight that. Now that means whatever we have considered was the first order analysis. Now let's slightly move to a second order one. So we have, let's say wherever we are getting the V control, you get that V control. This is VB, IN and IN bar. So we all know that in case when you switch the currents to one, so let me just call that, let's say this is 2 I naught. So at one time the current, depending on the swing, this will be I naught plus delta I and this will be I naught minus delta I. And so your VOP minus VON is VDD minus I naught plus delta I times, let's say this is Rn and this is Rp times Rn, and sorry, let me just call this as VON and this one is VOP, which is VDD minus I naught minus delta I times Rp. Okay. So can you comment if you're using this as a MOS transistor and you're having same control voltage, what about Rn and Rp? What can you comment on that? And all these transistors right now, we are considering the linear region. So I for R is actually Kw by L VDD minus V control minus mod VTH. Let's call the potential difference across the resistor as VR times VR minus, sorry, here VR minus VR square by 2. Okay. So I am just plotting that. So with respect to VR, this is I. Okay. So you see that this particular region is not a linear region. You are having a parabolic shift here. Okay. So if I just focus on this part where both my transistors are operating, right? So you can have so this is a linear one, and the actual one is, sorry, let's say, so let's consider only this. Oh, I versus VR. Okay, and we know that the left and right branches, they are operating at different VRs from a nominal point. VRN and VRP. Let's say you pick up some point which is VR0. So now I ask, means after giving you all this information, what is the relation between Rn and Rp? Let me just put equal or not equal. They are not equal as such. Okay. So the swings which we were considering as much more linear, they will not be any more linear just because of the resistance. Okay. So what can be done? Okay. So this is one thing, that your resistance Rn is not equal to Rp because of the secondary square law variation. That is one thing. The other thing, let me ask you another question, that if I am having a noise, now because this is an oscillator, you also look for the PSRR that we looked at an oscillator performance matrix. So yeah, I am having a right noise on this. Okay, so if, let me just consider two cases. If Rn is equals to Rp and your common mode rejection ratio of this cell is some finite. Finite means it's not like infinite common mode rejection ratio, which you will have only in an ideal case. What do you think about the supply noise coming at the output? Oh, so, yeah. Pardon? Will be? It will not, because the common mode change, right? So it will not show up. Your PSRR will be really good. Excellent PSRR you have. Okay. You reject all the noise because that is going to appear as a common mode noise. Now, if your Rn is not equals to Rp, okay, and again finite CMRR, common mode rejection ratio, in that case your PSRR will be poor for this particular set. Okay, so you see two things which I am considering here. One is that your output swing is actually dependent on the resistors. So as the current is different in the two branches, your resistance values are different, so your output swing is going to be different. Okay, and that is more non-linear in this case. So if I, so these two problems you understood which I focused here, right? So let's now begin what happens. So in one case, your VOP, so okay. So let me just again show this part. So in case with your VRN and VRP, right? You see this as a parabolic curve, which is not the linear. So your delta R are different. That is, VOP is VDD minus I plus delta I times R naught plus or minus delta, whichever you can say, delta Rn, and VON, VOP I put it this way, right? Okay. Yeah, this is VON, and VOP is VDD minus I minus delta I times R naught plus delta RP. Okay, so this delta R naught I just use as a at VR0, and this delta Rn delta Rp are not actually equal in this case. So you will see a non-linear output swing with respect to VR. Okay, but the thing is that at a given oscillation frequency, you are having a given I naught current, or whatever, you can say you are switching all the I. So whatever amplitude you get, that amplitude will be fixed. Is that it doesn't change, it is not linear with your oscillation frequency as such. Okay, that is the part. The other thing is your PSRR is going to be bad. That you can work out that how the noise actually translates. Okay, so both of these drawbacks can be overcome by using another kind of load which is called as Maniatius load. So let me show you. In place of the resistance, you use, this is VDD, this is V control for this load, and you can say this is I. Potential difference across the two is VR. So what is this? If you plot the I versus VR characteristics for the same, so this is VR, this is I. So let me say if VDS is equals to 0 in this case, which is VR is equals to 0, what will be the current through this transistor I1? I mean, this will be the same as what we have seen as a square law with respect to VR, right? So this will be something like this, okay? And if you're considering all the square law parts, so let me make it in a more ideal fashion that once it saturates, it actually becomes constant. And this voltage will be your VDD minus V control minus mod VTH. Okay. And what is the current which will be in the second transistor? So this is I1 and the current through this is I2. So current through I2 as per the square law, this will go something kind of this. This is your I2. Okay. There will be regions where you have, this is a VTH, mod VTH. So if you add both of these currents, you will have some, so it depends on all the parameters. You will have something and many a times I see that it is drawn as, let me just draw the way, means, so this is very specifically to show you that if you use a square law, there will be a linear region here. Whereas quite often we draw it like this. This is a straight line and slightly, okay. So let me draw with a different color so that it is, so this straight line is just an okay, and all these whatever these values is, you can work it out using the linear and saturation region, VR and I. This is total I. Okay. Now the interesting part for this kind of load is that, so let me say for current I plus delta I. So okay, I plus delta I you consider in this region, I plus delta I. Okay. And I minus delta I you consider in this region. Let's say this is the wall for that, because it's symmetric about this point. Okay. So you see at I plus delta I, your resistance. So now we are writing the same. VOP is equals to VDD minus I minus delta I times R1 or RP, and VON is equals to VDD minus I plus delta I times Rn. You work out both these Rp and Rn and substitute it. You will find that the variation with respect to delta I, right, because it is symmetric on both the sides, is very less. Okay, so if I write, there are three regions. First, when your VR is less than mod VTH, at that time total I is, and the thing is both these MOSFETs are equal sizes, W by L and W by L. This is called as Maniatis cell, and Kw by L into VDD minus V control minus mod VTH times VR minus VR square by 2. Okay, this is the first region. Another region of operation is VR is greater than equals to, sorry, VR is greater than equals to mod VTH and less than VDD minus V control minus mod VTH. At that time, total I is Kw by 2L into VDD minus V control, so it's L only, not 2L, minus V control minus 2 times mod VTH times VR minus, sorry, plus VTH square by 2. Okay, this you can work out, and this proportional to VR is the linear region which I was showing you here. Okay, and the final one is when your VR is greater than VDD minus V control minus mod VTH. At that time, you are having Kw by 2L into VDD minus V control mod VTH whole square plus Kw by 2L into VR minus mod VTH whole square. Okay, so if you work out all these, it means this is the current equation. Now you work out what is the incremental resistance. Let's say delta I is this value minus delta I, and you go plus delta I, and you find what is the incremental resistance at both the places. Okay, so for those incremental resistance at both the places, you will find they are the same. Now, if the change in the resistance is the same in your left and the right branch, right, then your power supply noise will appear as a common mode noise to an extent, and you will have a better PSRR. So symmetric nature in Maniatis cell, TIS cell, actually leads to you better PSRR. Yeah, any question? Let me stop here. I'm already out of time. We can discuss it tomorrow if there are any questions.